Okay, so let's move to the lecture 5, diffusion in crystal imperfections. So in lecture 4, actually we put more emphasis on diffusion in metal or ionic materials. But the crystal structure actually we assume they are single crystal material, right? So we didn't talk about there's a defect or grain boundary or free surface inside these materials, right? But in real case or in most of case, the material we deal with for sure have some crystal imperfections. For example, what's the crystal imperfections? For example, like the point defect, dislocations, or grain boundary. So I draw a picture. I grab a pictures here. This is polycrystalline material. So you have a grain, and in between two grain, you have a grain boundary, right? Okay. So in this case, how can we modify the diffusibility of materials of this kind of polycrystalline materials? Or how can we estimate the diffusibility in these polycrystalline materials? So the only one direction, the only clue or only information I learned from lecture 4 is the diffusibility inside the grain can express like this, right? It's a gamma total jump rate times mean jump distance divided by 6 times correlation factor F. So this is a diffusibility to describe how the atoms moved, how fast the atom moves through this grain. But if the materials you have is like this polycrystalline materials, then you have the atom here, right? So how the atom diffuse through this material will be like, for example, like this, right? I'm an atom here. Dun, 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 dun. Yes, I diffuse through the grain. Then probably I will jump into the grain boundary and move along the grain boundary. And for 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 some reason, I also jump. Then I jump inside the grain. So sometimes I will jump in and out of the grain, in and out of the grain boundary, jump from the grain boundary into the grain, or jump from the grain into the grain boundary. So in this case, how can we estimate the diffusibility of this type of materials? How can we do that? So I'm going to show you how to modify or how to estimate the diffusibility in this type of materials. And the diffusibility the diffusibility of this type of material, the diffusibility we talk about, some people also call it as the effective diffusibility. Use this symbol to represent the effective diffusibility. So what's the effective diffusibility means? It means the effective diffusibility is a measurable diffusibility of these materials, and also a combination diffusibility of these materials. Okay? And in this lecture 5 can simply classify into two parts. The first one, we will talk about the grain boundary diffusion. I want to show you how the atoms diffuse through the grain boundary, how fast it diffuses through the grain boundary. So in this part, we will introduce the term we call effective diffusibility. It's a measurable diffusibility, okay? And for the case we just talked about is the polycrystalline materials. And obviously, there's two diffusion paths for the atom can diffuse through this material, right? The one is through the grain, the other one is through the grain boundary. And so the effective diffusibility is related with the different diffusion path, how many diffusion paths you have in these materials, and also the volume fraction for each for the grain and grain boundary. And next, we are going to introduce you three different grain boundary diffusion mechanisms. And the second part, would be talk about the surface dislocation diffusion and surface and dislocation diffusion. But in this part, actually, inside your textbook, it just gives you some research data and some simulation results to describe the importance of the surface and dislocation diffusions. So in lecture 5, actually, we are going to address more in grain boundary part. So let's start here. So diffusion in crystal imperfections. So if you, so probably some people will ask about, oh, you already learned it from previous part. If you want to describe the atom diffused through materials, and you want to express this in energy as a function of location, so probably you will draw like this. When the atom at inside the grain, it want to diffuse from this location, or it want to move from this location to this location, it need to overcome the energy barrier, or some people call it as activation energy. But when we talk about the diffusion in crystal imperfection site, first of all, you need to know the diffusion path of the crystal imperfection site will include the dislocation internal interface between two phases, and free surface is the surface of the materials and the grain boundary. So in this case, the grain boundary, we take the grain boundary as an example. When the atom locates at a grain boundary, it belongs to the energy will be higher and metastable at the grain boundary side. So due to have a higher energy, so it will result in the smaller activation energy to allow this atom move from this location to this location, right? So because it has a smaller activation energy or migration energy, so the diffusivity will be higher. So this type of a diffusion path will belongs to short circuit diffusion. Means if the atom diffuse or move along this grain boundary or along this crystal imperfection side, they will move faster. So some people call it as a short circuit diffusion. So diffusion in crystal imperfection size, we want to introduce you some spatial term we call a characteristic diffusivity. So what's the characteristic diffusivity? It means the diffusivity along specific diffusion path. For example, like diffusivity inside the grain, diffusivity in the grain boundary for specific path, just only one path. So this kind of diffusivity we talk about is we call a characteristic diffusivity. And as you know, the valence fraction of crystal imperfection site in your material is play a very important role in diffusivity. So the capacity of the available diffusion channel is quite important. It's relative to the valence fraction of crystal imperfection site in your materials. So the defect density or defect fraction is quite important in this case. So let's talk about the characteristic diffusivity first. So as I mentioned, characteristic diffusivity in crystal imperfections means we just point out what the diffusivity along one diffusion path. So here we have a figure here. The vertical is a log diffusivity, and the horizontal axis is a reduced temperature, which means the melting point divided by the temperature. And we take this as we take a look here. when the T equals to melting point, and what we have here is equals to 1, right? So when the temperature is higher than melting point, the diffusivity we talk about, the characteristic diffusivity we talk about will be the diffusivity in liquid. When we try to decrease the temperature, then we can see there are several characteristic diffusivity, which means a diffusion along different paths, diffusion paths, right? And if we take this temperature as an example, we just focus on here, we find the lowest diffusivity one is a DXLO. So what's a DXLO? Actually, it's a diffusivity in bulk materials. Actually, this means the diffusivity inside the grain. We call it as a DXLO. And then we find the diffusivity increase. And as you know, compared with the grain, the diffusivity in the crystal imperfection side is higher than that in the grain, right? So when we move here, this one is we call the DD. So what's the DD? Is this diffusivity along a dislocation core, and we also label it as a dissociated dislocation. And if you move upward, you find that it's a DD, also DD, right? And this is undissociated dislocation. So what this means? We have a dislocation, for example, the Burgers factor like this. This is a whole dislocation. This is Burgers factor. This we call an undissociated dislocation. And dissociated dislocation like this, we can decouple this Burgers factor into these two small Burgers factor. And one of this one we call a dissociated dislocation. So based on this, you know, the undissociated dislocation has higher lattice distortion compared to the dissociated ones. So based on this one, the lattice distortion, you got a higher lattice distortion. So the energy for at this region will be higher. So the activation energy will be smaller. So the diffusivity will be higher. Okay? So this is explain why the DD undissociated one has a higher diffusivity than that on the dissociated one. And then the diffusivity along grain boundary also higher than DD dissociated one. This is a grain boundary. And the highest one at this temperature will be the diffusivity along the free surface. Okay? So based on this, we already confirmed that based on the experimental results, you find that the diffusivity in the crystal imperfection side are larger or higher than that inside the grain. And this is consistent with what we have here, right? Because the atom at this crystal imperfection side with a higher energy, so that will lead to the smaller activation energy, so that will lead to the higher diffusivity. Okay? Okay, so that's back to these figures. So regarding to this is a log D versus 1 over T. So the slope actually is related with the temperature depending term. So the delta H enthalpy depending on the type of crystal imperfection. So you can observe the slope will be different in different type of crystal imperfection site, which implying that we have different enthalpy here. And don't forget D diffusivity can express like a D0 times the temperature dependent term, right? And some people also write down write down substitute delta H enthalpy term as a melting point. Because in most of case, if you have a higher activation energy, higher energy barrier, the melting point of this material will be higher. So there's a proportional relationship between the enthalpy and also the melting point. Okay, so today we just ended here.